Hello everyone, my name is Jason Gregerson, and this video is going to be on solutions of linear systems via row reduction. So in the last video, we introduced reduced row echelon form and row echelon form, our REF or REF. So we took some matrix, like this matrix, and we did some elementary row operations to put it into this form. We call that form reduced row echelon form. So one big question we had last time was why? Why are we doing these operations in this matrix? What we can do is we can talk about this first matrix. We think, what happens if this came from a linear system? What happens if this was the augmented matrix of some linear system? For instance, if I had the linear system that looked like, then this would be the augmented matrix for that system, just like that. Now I know that by doing row operations, elementary row operations, to that augmented matrix, I'm not changing the solution set for that linear system. So the process of going from this matrix to this matrix, I haven't changed any of my solution sets to the system. But this last augmented matrix, if I looked at this one in system form, I could write out that system as x1 equals 1, x2 equals 2, and x3 equals 3. So I can see that once I've put that augmented matrix in reduced row echelon form, it's very easy for me to write out that solution. To summarize, if our matrix is the augmented matrix of a linear system, then the row reduction process leads to an explicit solution to the linear system. But in that last case, the system was very easy to write out. I just had x1 equals 1, x2 equals 2, x3 equals 3. I had one unique solution. But we know for linear systems, that's not always the case. In fact, we should recall that for a linear system, we could have no solutions, one unique solution, and infinitely many solutions. So if we now know that we can look at that row reduced echelon form as the simplification of the system so that we can actually see what our solution is, now we want to find out what characteristics of that reduced row echelon form lead us to see these three different scenarios where there's no solution, one unique solution, or infinitely many solutions. So to do this, let's investigate some reduced row echelon form matrices. All right, so now I have three reduced row echelon form matrices, and I'm going to take these as the augmented matrix of some system, and I want to see how I can look at these and talk about their solutions. So for the first one, once again, we have kind of a nice system. If I wrote out the equations for this, it would be x1 equals 2, x2 equals 3, and x3 equals 1. So a very nice solution again. So if I look at this system more carefully, if I look at this augmented matrix more carefully, I know that this first column, if I rewrote out the system, these are really all the coefficients to my x1 variable. And the second column are really all the coefficients to my x2 variable. And the third column are all the coefficients to my x3 variables in all the different equations. And that last column represents the right-hand side. So I can see that if I have an augmented matrix with 4 columns, I'm going to have 3 variables. Now in this case, all 3 of these variables are going to be basic variables. What are basic variables? Well, these are variables associated with a pivot column. So I see that all 3 of these columns are pivot columns because they all have a pivot position. There are my leading entries of each row, therefore these are pivot positions. Each one of these columns has a pivot position, so I'm associating the variables for those columns as I'm defining them to be basic variables. Now if I'm defining those to be a special kind of variable, there must be other variables. And so the related variable would be free variables. And these would be variables that are not basic variables. And so when we pair those two definitions, we can see that if the variable is associated with a pivot column, then it's basic. If it's not associated with a pivot column, it must be a free variable. Now these pivot columns are important columns. If we write out the equations, that pivot position is the leading entry of that row. And so I'm writing out the equations, that would be the first variable that's written. And since I have that variable in each equation, I could always solve for that variable. So if we look at the second example, that first equation is going to be x1 plus x3 equals 2. The second equation is going to be x2 equals 1. And the third equation just says that 0 equals 0, so it really doesn't give me any information. So once again, I have a pivot position here and here. These are associated with the variables x1 and x2, but I don't have a pivot column associated with x3. So x3 must be a free variable. And so this is how I'm describing my solution. So what would specific solutions look like? Well, if I'm thinking about maybe a set of points that have an x1, x2, and x3, so I have an x1, x2, and x3 value, and I'm just writing them as a list of numbers here. My solution tells me that x2 has to be 1. But what about x1 and x3? Well, if I chose x3 to be 1, then x1 would have to be 1 to make that first equation true. If I think of another possible solution, once again, x2 has to be 1. But this time, if I choose x3 to be 0, I can still have a solution, but x1 would have to be 2. So in other words, I have my solution. I just have to choose x3. x3 is free to be any value, but once I choose that value, then x1 becomes fixed. So x3 is my free variable in this case. And I can also talk about how many solutions there are. I've written 2 solutions out. I know there can't be just 2. If there's 2, that means there is infinitely many. We talked about that earlier. So the pivot columns are marking my basic variables. And if I have a column that's not a pivot column, those are identifying my free variables. And if we look at this case, we might want to assume that if we have free variables, then we must have infinitely many solutions. But before we draw that conclusion, let's look at our next example. The first equation says that x1 plus x3 is equal to 2. The second equation tells me that x2 is equal to 1. But the last equation tells me 0x1 plus 0x2 plus 0x3 equals 1. Well, this is never true. Thus, this tells us there's no solution to this system. But if I look at x3, if I look at that third column, it is not a pivot column. Therefore, x3 is a free variable. So it's not just the fact that we have free variables that lead us to infinitely many solutions. The system first must be consistent. So now we have these 3 cases: no solution, a unique solution, and infinitely many solutions. Let's see if we can tie all this together with our pivot positions. So what made this last system have no solution? The problem was I had all 3 coefficients to my variables were 0, but I had a non-zero value on that right-hand column. Now, since that was the first non-zero value, that's telling me that this is a pivot position. So the problem was this right-hand column became a pivot column. If the right-hand column is a pivot column, there must be no solution to the system. Now, as we can see in the first 2 examples, the first 2 systems, that right-hand column was not a pivot column. So therefore, there were solutions. The first 2 systems were consistent. And then what distinguished between one solution or infinitely many? It was the free variables. So to summarize all these ideas, we can look at the following. The following theorem says that a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That tells us when it's consistent. Now, if the system is consistent, then if there are free variables, that leads us to infinitely many solutions. If there are no free variables, this implies the solution is unique. Once again, that's only if the system is consistent. So we've talked a lot about reduced row echelon form, but what about row echelon form? Why did we define that? Well, if we take a augmented matrix, we'll start here, and if we do some row operations on the way to getting row echelon form, so for instance, to get to this next step, I would do a couple row operations. I would let R2 equal R2 minus R1, I will also let R3 equal R3 minus R1. And if I do those two operations, I get to this form. And then I take R3 equal to R3 minus 2R2, and I get to this form. And this is row echelon form. Now, what row echelon form does is it marks my pivot positions. It establishes my leading entries in each row, and it tells me what pivot columns I have. Now, if I were to take this form and go the rest of the way to do the backwards phase to get to reduced row echelon form, all I would be doing is using these pivot positions to eliminate values above them, but that wouldn't change the pivot columns. So the point here is once I get to row echelon form, I have established my pivot columns. And that's all I need to determine whether or not a solution exists and if that solution is unique. So once again, to summarize, solving the system is really just replacing one system with an equivalent one that is easier to solve. And we go from system to system using row operations. Row echelon form is just simplified enough to determine whether or not there is a solution and if it is unique or not. Reduced row echelon form allows us to form our solutions, and each matrix is row equivalent to one and only one reduced row echelon form. Now let's tie everything together by going through an example problem. Our solution process says write out the augmented matrix. So to do that, we will have 1, -3, 5, and 0. That represents that first equation. And the second equation would be 0, 1, 1, and 3. The next step says to put the augmented matrix in row echelon form to see if it's consistent. Lucky for us, this one's already in row echelon form. So I can look at my pivot positions right here and here, which means the first two columns are pivot columns, but the third column is not, and the last column is not. So since the right column is not a pivot column, the system is consistent. We have a consistent system. We have solutions to our system. Now, is our solution going to be unique, or are there going to be infinitely many solutions? Well, because column 3 is not a pivot column, that tells us that x3 is a free variable. So we have a consistent system with free variables. That tells us we should have infinitely many solutions. Now let's see if we can find those infinitely many solutions. So we've gone to row echelon form, and we understand what kind of solution we expect to get. Now we'll go to reduced row echelon form to find all those solutions. So I'm going to take R1 and let that equal R1 plus 3 times R2. R2 will stay the same, and row 1 will turn into this. And now I can write out my solution. The first row tells me that x1 plus 8x3 equals 3. And the second row tells me that x2 plus x3 equals 3. Now I want to write out my solution as x1 equals something, x2 equals something, and x3 equals something. That's how I like to see my solution. When I solve that first equation for x1, I see x1 equals 3 minus x3. I solve the second equation for x2. x2 equals 3 minus x3. I know I can solve that first equation for x1, and I know I can solve that second one for x2 because those are my pivot positions. Those are the leading entries. But now there is no third one. x3 is a free variable. So x3, what does that equal to? Well, it's just a free variable. Now when I write out my solution like this, having solved for my basic variables, I'm going to call this the parametric description of the solution. It's a way I can parameterize the solution. You choose a value for x3, and I will be able to give you a value for x1 and x2. And it's set up to do that because I've solved for my basic variables. So when we solve for our basic variables and write our solution in this form, once again, that's the parametric description of the solution. And that concludes this video on solving linear systems via row reduction.